Hello, everyone, and welcome once again to Cape Coast. And I hope you are enjoying the city. I am Felix, and together with Surveyor Abdul Wahab, we are presenting our work on identifying flood-prone areas in Ghana from Earth observation data. Now we go straight to introduce our work. Now, a flood, as we know, is the presence of temporary surface water that occur through rainfall or spillage from a dam or overflow from the banks of a river that appear stay for a short period of time. And this is different from permanent surface water bodies such as rivers and lakes that stay on the surface for a longer period of time. Now, flood is a recurring problem in Ghana, and if I'm not wrong, it has been occurring for the past centuries. Almost every year, there is flood in Ghana, having devastating impacts on our communities and livelihoods. Now, the major drivers of flood in Ghana has been attributed to climate, poor urban planning and development, and inadequate drainage facilities. However, we hypothesize that the topography of the country at a national scale could also be a major contributing factor to the flood situation. Now, most flood-related research are concentrated on Accra due to the economic potential of the capital city, leaving many other areas and regions understudied. And to have a holistic view of the flood situation in the country, we want to use Earth observation data sets to study the phenomena on a national scale. And this is inspired by visualization of the day and night movement of precipitation clouds on the UMESAT web platform. Now we just saw the night, and then now we are seeing the day time movement of the cloud, and we see the white pixels which represents the precipitation carrying clouds moving from East Africa East Africa towards West Africa. And we see that the white pixels cover completely the whole of Nigeria, Benin, Togo, and then also Ghana and Cote d'Ivoire as well. And then also covering major parts of the Atlantic Ocean. So our fathers who go to sea, as I used to be in time past, are at risk of rainfall. Now, some other communities different from Accra that also are affected by flood include Mori, closer to Cape Coast here, and Kodiakrom in Kumasi, and then also in central region near Cape Coast. There was an incident that happened on Friday, June 17, 2022, where due to heavy rainfall, the Surrey River overflew its banks, and the only bridge that connects Cape Coast and Trefopraso got destroyed as a result of the overflow. And commuters between these two communities had to use alternative routes until repair works were done. So flood occurred not only in Accra but other areas in Ghana as well. Now the objective is to identify the spatiotemporal pattern of precipitation and flood in Ghana using Earth observation data sets, and to analyze the spatial relationship between flood and topography of the country. Now the study area is Ghana on the national scale, and we know the countries surrounding Ghana, the administrative regions, area, and then the population. So I will not spend so much time on it. And on the image on the right, the most significant feature we see is the Lake Volta. This one. And the Lake Volta happen in between eastern region, Oti, Bono East, and then part of Savannah regions. And then we also see the Lake Bosomtwi in Ashanti region. And there are other surface water bodies, including rivers such as the Densu River in the country. And on the image on the left is the elevation profile of the country. Now, the most significant feature that we see from here is this Y-shaped kind of mountain that sits beneath the Lake Volta. and the Y-shaped mountain has its tail towards the western part of Greater Accra region. Now, the topography of the country is a mix of low-lying plains with higher altitude areas and elevation ranging between minus 69 meters to 872 meters above mean sea level, according to the Copernicus datasets, DEM data. Now, all the maps that I'm using are represented in the Ghana National Grid CRS, Coordinates Reference System. Now, the country also has two major seasons: the dry season between November and March, and then wet season between April and October. Now, the northern half of the country usually experience a higher amount of higher mean temperature as compared to the southern half of the country. And this image that we see is the mean temperature between 2020 and then 2024. However, although the southern half of the country is at a lower temperature as compared to the northern sector, Ashanti region has Kumasi, which has a higher amount of temperature, whereas Greater Accra region and then Volta regions also have higher amount of temperature in the southern sector as compared to their immediate neighborhoods, and these are due to urban heat island effects in these communities. And the southern sector also experience sea breeze, which help with the cooling effects of the southern sector. And then the Lake Volta and other lakes also provide cooling effect to their immediate neighborhoods as well. Now, the data that we are using is the Copernicus Sentinel-1 for the flood detection, and the ESA world cover for and then Copernicus DEM for refining the flood mask that will be obtained from the Copernicus Sentinel-1, and then the integrated multi-satellite retriever for global precipitation measurement for determining the temporal profile of precipitation in the country. And the UMESAT data was used for the selection of the pre-event and the post-event period for the flood studies. Now, the Sentinel-1 is a synthetic aperture radar instrument that works by sending signals onto the surface, and depending on the characteristic of the surface, it records the returned signal, the intensity, and then the phase of the returned signal. And the signal, when it encounters a smooth surface, the smooth surface reflects the signals away from the radar, so there is a reduction in the intensity of the returned signal. And this is as we see, for instance, on the map over here. So here we see that the signal intensity is reduced upon encountering a smooth surface such as water surfaces, and with such smooth surfaces also they appear dark on the sentinel image. Now, when the signal encounter a rough surface, the rough surface return the signal towards the satellite, so there is an increase in the intensity of the returned signal, and this change in the intensity is what is used for maybe change detection such as flood, or flood, to detect the temporary change in water surface on the ground. Now, we first use the image dataset to compute the total daily rainfall from the 30-minute rain rate measurements for each day between January 2015 and July 2025 over the whole of country. So the daily total rain rates over the whole of Ghana, and this was used instead of the average, because it might rain on some parts and then not rain on some other parts of the country. And so if we find the average, we might have the signals cancelling out. And the flood detection was carried out using this method by first selecting the pre-event period and then the post-event period. The pre-event period between 13th and then 23rd of December 2024, and then the post-event period between 6th and then 9th of July 2025, last month. And these periods were selected because using the UMSAT web platform, we found that between this post-event period, there was so much precipitation covering or engulfing almost every part of Ghana. Whereas in the pre-event period, there was little to no rain in Ghana. Now we used the Sentinel-1 and then made a filtering for the instrument mode, the receiver polarization, VV, vertical transmit, vertical received polarization, ascending orbit pass, and then 10-meter resolution. And then we filtered for the post-event and then the pre-event periods. After doing this thing, we then applied the Lee speckle filter to remove the white pepper noise usually common in SAR images. And because the intensities recorded in the SAR images or the SAR instrument is in decibel logarithmic scale, it is converted to natural scale in order for mathematical operations to be performed. So after doing the conversion, then we did a change in detection using the ratio approach. So the post-event divided by the pre-event images. And then on the diagram on the right, we see the distribution of the ratios that we obtained after doing the computations. And here a value of 1 indicates that there was no change in the intensity. A value more than 1 indicates that there was an increase in the intensity, so corresponding to a rough surface. And then a value less than 1 indicates that there was a reduction in the intensity of the signal. And so here we can see that most of the signals have a reduced signal, indicating the presence of surface water bodies. And then after using this frequency distribution, we then define a threshold of 0.75 instead of 1 in order to make room for reductions due to other causes such as the change in maybe land cover features and those kind of stuff. After doing the ratio and then the thresholding, we then refined the flood mask for areas that we excluded permanent surface water bodies from the flood map, and then we excluded areas that have elevations above 330 meters above mean sea level, and then we also excluded areas that have slopes more than 10 degrees in order to have the final flood map. Now to the results. First, we observed the temporal profile of rainfall over Ghana between 2015 and then 2025. And most significant on this image is this region, where we have higher amount of rainfall, total rainfall over Ghana. And so in these regions occur in 2021, 2022, and then 2023, implying that during the COVID time there was high amount of rainfall over the whole of Ghana. And the other years almost have the same high amount of rainfall. And another thing that we can see from this image is that in between the years we have the highs and then the lows. So, and these highs and lows repeat, so representing a seasonal cycle, annual seasonal cycle. And the highs happen almost during the middle half of the year, whereas the lows occur getting to the end of the year and then the beginning of the subsequent year. And this aligns perfectly with the climate profile of Ghana. and also other parts of West Africa. Now to the flood, potential flood map. Now this is the potential flood map that we obtained. The red regions, such as these ones, represent the potential flood areas. The blue regions represent the permanent surface water bodies. The violet represents the slopy areas, and then the green represents the areas that have elevation above 330 meters above mean sea level. Now on the map we can see that the red pixels are very few on the northern half of the country, whereas on the southern half of the country they are much visible, so implying that there is less flood occurring in the upper parts of the country as compared to the southern sector. Now in the upper part also we see that some communities have flood or red pixels that are concentrated, so flood areas that are much concentrated, so areas like Tamale, and then the eastern part of Upper East, and then Laura, Dapola, and Babylon communities on the western part of Upper West. Now on the southern parts, for the areas beneath Bono East, and then Oti regions, we can see that there is a uniform spread of the red pixels in western north and then western regions. And then in Ashanti region is also uniformly spread, but in Kumasi over here we see that it is much concentrated as compared to its neighbors in Ashanti region. Similar thing also happens to eastern region. The flooded areas are much dispersed, spatially distributed, and not so much concentrated. In central region we see a few amount of flood as compared to, for instance, western region, and then Ashanti region, and then eastern region. However, on the northern part of central region, so the areas between Dunko and then Diaso have high amounts of rainfall as compared to the areas beneath central region in these communities. Now to Greater Accra, we can see that on the western half of Greater Accra, so the areas that sit beneath the white tail of the mountain that we saw, this one, the areas that sit beneath this white tail, and then areas around the Wager Dam have higher concentrated flood as compared to the eastern half of Greater Accra region. Now by determining the amount of the amount of rainfall, flood areas, so we summed the area of the pixels in each of the regions in order to make the comparison. And here we can see that western region, Ashanti region, eastern region, and then central and western north have high amount of flood areas, with western region leading. So there is so much flood occurring in western region, and this is even much higher than that of Greater Accra, and is probably because of the smaller size of Greater Accra as compared to the other regions. Now the other regions are at almost the same amount of have the same area of flood. However, northeast and then Oti regions have reduced or smaller, the lowest amount of flood for the period considered. Now we try to relate the flooded areas with the topography of the country. Now by making a vertical cut through the terrain of the country, so from Komenda through Kumasi to Wuru in the north, at this eastern coordinates, we see the elevation change of the country. So the elevation does not have a uniform slope, it is undulating, and we can see that the northern half of the country is at a higher elevation than the southern half. So in case there is any rainfall, the rain will move from the northern half towards the southern half, from the northern part towards the southern part of the country. And this mountain over here represents this mountain beneath Lake Bosomtwe. The mountain over here represents the part of the Y-shaped mountain that we saw. This one represents this mountain over here in Bono East, and then this one represents this mountain area that we see over here. Now Lake Volta sits in between these areas, so then water flow from these mountains will be captured in between these mountains, and then they will be captured into the Lake Volta. And then also Kumasi, which sits in between Lake Bosomtwe and then the Y-shaped mountain, so somewhere around here, sits at this elevation. So by intuition, rainfall from or surface runoff from the top of these mountains, this one, will have an immediate contact with the community of Kumasi. And also due to its urban potential or its urban development, we see much concentrated flood in Kumasi as compared to other areas in Ashanti region. Now to Accra, where we have so much flood on the western part of Accra. Now beneath the Lake Volta sits the Y-shaped mountain, and this is Lake Volta, and then the Y-shaped mountain is somewhere here. Now the Lake Volta has two major outlets, one on the eastern part and then one on the western part. The one on the eastern part serve feed the Akosombo Dam that is used by the Ghana Water Company to provide electricity. The Ghana Electricity Company, the Electricity Company of Ghana, to provide electricity to the country. Whereas on the western part, it feed the Densu River, which runs through towards the south, towards the Densu estuary that is found between Botiano and Mpwaeso on the western part of Greater Accra. And the Densu River also intersects the Wager Dam, and around the Wager Dam we have the water treatment plant of the Ghana Water Company, which provide water to Greater Accra and its neighborhoods. And so rainfall from the Lake Volta towards the eastern outlets is controlled at the Wager Dam. However, on the western outlets, there is not so much control, and so a high amount of runoff from the Lake Volta through the Densu River and then the Wager Dam overflow the banks of the Densu River and then the Wager Dam, and so we see so much concentrated flood on the western part of Greater Accra. So that's why we have so much flood on western part of Greater Accra most of the time in the areas around the Wager Dam. Now the limitation of the study is that only remote sensing data is being used, so ground validation data was not used for this purpose. However, we confirmed some of the flooded areas in such as Mori, Kumasi, and then Upper East by personal experiences in those kind of communities. And then also waterfall on rooftop might also be classified as flooded areas, and these ones were not excluded from the flood mask because in Ghana the buildings, some of them are at intervals less than 10 meters, the spatial resolution of the Sentinel-1 data that we are using. And so if we are to exclude the rooftops, we might end up with removing also the flood areas as well, so we had to leave them. However, maybe in case if there is any high resolution data set from, maybe for instance, UAV, it could be used in order to improve the accuracy of the work. Now, to conclude the work, we successfully used Sentinel-1 to map flood on the national scale, and then the temporal profile of rainfall that we observed aligned perfectly with the weather pattern of Ghana, and the flood that was detected also fall on the wet season of Ghana. And then flood also has an annual and then natural occurrence in conformity with the climate pattern of Ghana, and it is not uniform across the country. It affects some of the countries more than others, and it's related also to the climate and then the topography as well. Now, to the recommendation, considering that the flood has a natural and seasonal cycle of occurrence, temporary solutions are implemented. So every year we might say that, oh, there will be flood in this area at this period, so prepare yourself. But this is a temporary solution, and on the long term it does not help. It's not a sustainable solution, and there is a need for engineering, advanced engineering solutions in order to reduce the risk of flood or the impact of flood on the long term. And we can take initiative from countries such as Netherlands, Japan, and then Italy. Netherlands, for instance, sits beneath the mean sea level, and so it's at a higher risk of flood. However, its government implemented the Delta Works project made up of river barriers that block the flow of water towards the communities, and this has helped protect the land of Netherlands for a period of time. Japan also has issues with flood, and so they also implemented the JCANS project, in which surface runoff from the top of the surface is redirected through underground tunnels before it is finally released into maybe under water supply bodies. And Italy, the video that we saw on the right over here, also is the MOSI project implemented in Venice in Italy, and Venice has been at a high risk of flood from the tidal influence. And finally, we can also integrate scientific approaches and early warning systems and predictive models. However, those kind of models might not be sustainable on the long term, and so there is a need for advanced engineering measures in order to reduce the impact of flood on our communities. So thank you very much, and your suggestions are more than welcomed. Here is my email. In case of any feedback or any comments, they are more than welcomed, and I'll get back to you. Thank you very much, and have a good time.